So all we're doing is analyzing motion by breaking it apart into x and y axes. You've got experience with breaking up vectors. Today is 11:29. And now we're going to do that with motion. If it's moving under anything, under no force but gravity, it's projectile motion. The acceleration is all happening on the y. And we can use our 4 equations to break apart the motion and look at where the object is going. So because on the horizontal axis there's no acceleration, its motion on the x-axis doesn't change. There's no change in x velocity. Okay. Do we want to do sample problem 3D together, though that was done in the video? Did you copy it down? Did you? Okay. So one of the assumptions that we make with horizontally launched projectiles is that whatever velocity we start out with on the x-axis is the same velocity we finish with on the x-axis. So the initial, the final, and the average are all identical. Well, what causes a change? What do we call a change in velocity? Right, acceleration. Well, this is true as long as acceleration sub x is 0. There's no acceleration on the x-axis. Now, is this 100% true, or are we fudging things for high school physics? We're fudging. Yeah. If you are heading into engineering, you're going to have to factor something that we're ignoring to make things easy. What are we ignoring? Air resistance. Yeah, friction due to the air around you. At the level of calculations we're doing, we don't factor in air resistance because it's too complicated. So we assume that there is 0 acceleration on the x-axis, nothing slowing this thing down, nothing speeding it up. You'll hear me say, does it have a rocket strapped to its butt? No? Okay, then acceleration on the x is 0. As long as that's true, then these things are all equal. And that makes a lot of our calculations a lot easier. We'll go, this is practice problem number 34 out of the book. Fastest recorded pitch in Major League Baseball thrown by Nolan Ryan in 1974. If this pitch was thrown horizontally, so there's this pitch. If it was thrown horizontally, the ball would fall 0.809 meters by the time it reached home plate, 18.3 meters away. How fast was Ryan's pitch? So here's what we have to address. We have some amount of motion on the x-axis and some amount of motion on the y-axis. And those are combining to give us that whole little sort of parabolic, I do a terrible job drawing parabolas, that projectile motion thing. We can make it a little bit better, like that. So what we're being asked is how fast was Ryan's pitch? We're looking for VI. They're saying if this was thrown horizontally, straight out. So that would be VIX or VIY? VIX. So this is VIX, and we know that VIX is going to equal VFX, and it's going to equal VAX. Velocity on the x-axis is not changing. What's the VIY? 0. Yeah, there is. These are horizontally launched projectiles. There is no initial velocity on the y-axis. That's important because, of course, you know we're going to change that up next week. We're going to introduce problems where there is an initial velocity on each axis. Okay, so to start solving this, I'm going to shrink all this. Best thing to do is to list your variables on the x and y axis. This makes it a whole lot easier because you can see where each variable comes from. Okay, so Vx, well, that's what we'd like to know. Okay, so V sub x is what we want to know. We know that VIY equals 0. And that's important. Okay, we're also given this piece of information. We're given the distance on the x-axis. We're given the distance on the y-axis. Can we use those? Absolutely. So we have a delta x of what? Let's see. Delta x is 18.3 meters. All right, so we've got Vx, we've got Viy, we've got delta x, we've got delta y. Let's look at the x-axis for a minute. If the velocity is constant, do we have anything else? No. There's no acceleration. Now, we can write that, if it makes us feel better, a sub x equals 0. You don't have to, but I sometimes do to remind myself of that fact. On the y-axis, we've got a Viy. Do we have acceleration on the y-axis? Yeah. So acceleration on the y-axis is going to be equal to, okay, so we've got acceleration on the y. What do these axes have in common? What is the thing that bridges the axes and connects the motion happening on the axis? Time. Time is your bridge. So we know that no matter what, for every moment of motion, there's an x velocity and a y velocity. There's an x position and a y position. So time is that bridge. So what we can do is use the bridge of time, and looking at the variables that we have on the x-axis, how do we create an expression that includes time? You're going to get really good at this. Vx equals delta x divided by delta t. Okay, and I'm just going to kind of sit that there for a moment. Now, on the y-axis, I have Vi, y, I have delta y, I have acceleration on the y, and I have time. Do I have an equation that connects those four things? Okay, so what equation can we use on the y-axis to connect those four things? It's my favorite. Delta y equals Viy plus 1/2 a sub y delta t squared. So the question is, is it always going to be these two equations, basically? Yes and no. While we're doing horizontal projectiles, these tend to be the two fallbacks, and these are the ones that are most commonly used. I can't readily think of a problem where you can't use these two as your base. Now, this works in horizontally launched projectiles for one simple reason. Because Viy, and this should be a subscript, it looks bigger than it should be, is 0. What did I do there? I left out delta t. Geez Louise Moser. Viy delta t. So it works nicely in these because of the fact that Viy is 0, and that goes away. Okay, so what that allows us to do is then solve this equation for delta t and plug it in to there. So we've solved our equation for the x-axis for t, and we're going to plug it right into our equation on the y-axis. One thing I didn't do is I didn't make a little subscript y for my acceleration. You don't have to do that. Because in projectile motion problems, we know there's no acceleration on the x-axis, but if you feel you're at risk of forgetting that at some point, by all means put in a little a sub y. I don't generally do it. I'm kind of doing it right now to reinforce the notion that all the acceleration is happening on the y-axis. There's no acceleration on the x-axis. Okay, so We've got delta y equals 1/2 acceleration on the y times the quantity delta x over v sub x, quantity squared. Now, I mean, the tricky part, but it's not all that tricky, is that we have to solve for v sub x. So what do we have to do first? I'd rationalize that fraction. We're going to like really go step by step, not skip any steps. The first thing you have to do is distribute that squared. So we have delta x squared over v sub x squared.